So today we're going to look at a number of ways to improve our estimates using triangles. And the first thing that we're going to look at is different ways to arrange the rectangle using what's called a midpoint sum, using a different shape, which will be a trapezoid sum. And now we're going to do the long-awaited increasing the number of rectangles to infinity. That's going to be one of our goals today. All right, so to start with, the midpoint sum. So here's our problem. So these are a little bit easy to clean off. So I want to estimate the area under x squared from 0 to 2. I'm just working with the same shape over and over again, just to show how these different methods compare. All right, using 3 rectangles in a midpoint approximation with 3 rectangles. All right, so what does that look like? First of all, I'm going to have 3 rectangles, and well, how wide are these rectangles even going to be? Like, what are my x sub i's here? I don't even know. So let me start by figuring out how wide those rectangles have to be. So delta x is b minus a over n, so that's going to be 2 minus 0, which is 2, over my n, which is 3. So the width, the delta x of each of these is going to be 2/3. So that seems a little obnoxious. But fortunately, there's only 3 of them. And by the way, the AP exam, when it gives you trapezoid, actually really when it gives you any of these rectangular approximations, it tends to only ask for 3 or 4 intervals, which means that sometimes the easiest way to do these is to draw them out. And that's what I'm going to do with this one, is just draw it out. We can talk about what kind of formulas you can use as well, but we'll do that later. Okay, now, what does it mean that we're going to use a midpoint approximation? These are our rectangles. This is the width of our rectangles. But we're not going to use either endpoint. We're going to use the midpoint of that interval. All right, so these values here are the edges of the rectangles, but they're not the x sub i's. So we can figure out what these are. I'm counting up by 2/3, so this is 2/3, and this is 4/3, and this is 6/3, which is 2. All right, so but what are the x sub i's that I'm actually going to use? I'm going to use this number, which is half of 2/3, which is 1/3. I'm going to use this number exactly between 2/3 and 4/3, which is 1. And I'm going to use the number in between 4/3 and 2, which is 5/3. So those are my x sub i's. Now you actually, it's a little bit arbitrary whether you call the first one x sub 0 or x sub 1. In the way I've been laying it out, I've been calling this one x sub 0. So x0, x1, x2. So then you can lay out your standard chart, I, x sub I, f of x sub I, delta x, a sub I, and yeah, so the I I'm going to call 0, 1, and 2. That's the part that's a little bit arbitrary, because I could call them 1, 2, and 3. I'm not really using either endpoint at all. So my x sub i's then are 1/3, 1, and 5/3. And then my f of x sub I, I'm still using y equals x squared, so I get f of x by squaring the number. So I have 1/9, 1, and 25/9. My delta x remains 2/3 throughout, 2/3, 2/3, 2/3. I multiply the f of x sub I times the delta x to get the a sub I, which are going to be 2/27, 2/3, and 50/27. All right, now I need to add those together. So if I want to add those together, probably the easy way to do it is to get 27ths as a denominator. So my 2/3 is equal to 18/27. And then, so yeah, 18 plus 2 is 20, plus 50 is 70. So so that adds up to 70/27, and I can say that my area that I'm estimating is approximately equal to the sum from I equals 0 to 2 of a sub I, which is equal to 70/27. All right, which by the way equals 2 and 16/27, an interesting number. So here's something that is an interesting thing to compare. So 2 and 16/27. Now one thing to bear in mind, I didn't draw the rectangles. I meant to do that. What do the rectangles actually look like? We're going at the midpoint of the interval and drawing the rectangle like that, right? So we're going to the midpoint of the interval. This is what your midpoint rectangles look like. It's 3 rectangles, and each rectangle is formed at the midpoint. So you can see the advantage of this method, right? This is the rectangle like this, like this, like this, 3 rectangles. So the advantage is, instead of all of the rectangles leaving part out, or all of the rectangles including extra, each rectangle leaves some area out and has some extra, leaves some out and has some extra. So it becomes, for a function like this, the estimate that you get becomes inherently more accurate. Look how with 3 rectangles, we got 2 and 16/27, which is already within the error bounds that we got for 8 rectangles, right? With 8 rectangles, we knew we had to be between 2 and 3/16 and 3 and 3/16, all right? This value is already between those two values. Now, the disadvantage is I don't know whether this is an overestimate or an underestimate, so I don't have any upper bound or lower bound. I just know that this is a fair approximation to that area. All right, so that's one thing we can do is shift where we're evaluating the rectangles. The next thing we're going to look at is using trapezoids instead of rectangles.